I'm Mark, and this is Euler's Melting Pot. In this challenge, we try to complete every Project Euler problem in a different programming language. Today, we're actually going to take a detour and have another look at Project Euler problem number 1. Specifically, and I can't believe I'm saying this, we're going to solve Project Euler problem number 1 in Infinite Craft. For those of you who don't know, Infinite Craft is an AI-powered sandbox game by Neil Agarwal, released a couple of months ago. We start with the 4 classical elements of earth, wind, fire, and water, and we're left free to combine objects to our heart's content. For example, if we take water and fire and put them together, we would get steam. We could then combine steam and wind to get cloud, or steam and earth to get mud. But here's the catch. Neil didn't hard-code these crafting recipes. The game goes infinitely deep, and if you combine 2 objects that nobody else has ever combined, the game automatically queries a large language model, something like ChatGPT, to figure out what object should be produced as a result. And that was where my interest ended for a while. I played around in this game, I had my fun, I discovered several new objects, including Justice Tangled, superhero memes, Super Cowboy Batman, and a headless Devore riddle, whatever that is. But at the time, I didn't consider this game a candidate for Euler's Melting Pot. Some games like Factorio or Minecraft have circuitry and electricity mechanisms that can feasibly be used to perform computation. And believe me, we'll be using both of those games to solve problems in this series sooner or later. But Infinite Craft isn't like that. It's just throwing text at a large language model. Surely it can't perform computation, and even if it could, it wouldn't be remotely consistent, right? There was one thing I did notice pretty early on. Infinite Craft seemed very eager to add numbers if it encountered them. For example, if you unlock the object 2001, which you can get through the movie 2001: A Space Odyssey, and you craft it together with another instance of the object 2001, you get the number 4002. Add another 2001, and you get 6003, then 8004, then 10,005, 12,006, 14,007, 16,008, 18,009, and finally 20,019. Appending another 2001 gets us back to the year 2020. So Infinite Craft will tend to add numbers, albeit with some error bars. The astute viewer will have noticed that 2001 plus 18,009 is not, in fact, 20,019. And the even more astute viewer will have noticed that 2001 plus 20,019 is not, in fact, 2020. But we can actually get a second shot at a lot of this. If Infinite Craft messes up the addition, we just have to find another object with a number in it to try again. We've worked with bare numbers so far, but we could have also done the same with 2001: A Space Odyssey, or Metroid Prime 4, or anything that naturally has a number at the beginning or the end. If you get desperate, you can even make up new movies like 2001: A Space Hippogriff. The key takeaway is that if our robot overlords mess up the arithmetic, we can just generate a new sequence of numbers and try again. So we can add numbers together, very slowly and in an error-prone way. But addition isn't quite all we'll need, and that's where I sort of stopped for a while. After all, if you ask a super intelligent AI completion framework with all knowledge of human history what you get when you put 2 and 2 together, logically it would probably say 4. But surely we can't phrase other mathematical operations as simple concatenations of 2 random objects, right? And yet there is some method to the madness. Certain words, like opposite, are perfectly obtainable in this game and act as a sort of verb when used on a more conventional concrete noun. For instance, opposite plus light is dark, and opposite plus red is green, the complementary color to red in the traditional red, yellow, blue subtractive color model. Another good example is the word verb, which generates a verb-like version of an object. Verb plus plant is grow, and verb plus book is read. So we can use verb to turn a noun into a corresponding action or verb. It's not arithmetic, but it's a step in the right direction. We can sort of apply unary operations now. Let's take a look at what we would actually need to do to solve a real math problem in Infinite Craft. Remember, we're jumping back into Project Euler problem number 1 today. That is, we want to calculate the sum of all multiples of 3 or 5 below 1,000. Now, a few years ago when we solved this problem for the first time, we did it in Golf script. And we did it in a fairly straightforward way. That is, we produced all of the multiples of 3 and all of the multiples of 5, took a set union, and then summed the resulting set. This is the equivalent code in Haskell. And suffice to say, I doubt this will ever work in Infinite Craft. Remember our limitations. We can probably add numbers, but if we want to apply any other operation, we're going to need to craft the operation itself together with an argument number. That limits us, generally speaking, to unary operations. That is, until someone can find a way to perform functional-style currying in Infinite Craft. But here, not only do we have a binary set union operator, we also have 2 lists, and I haven't even begun to consider how to generate lists in Infinite Craft. The funny thing is, we might not have to. 2 years ago, we were all amateurs, but we've grown up a lot since then. So let's take another look at this problem and see if we can simplify it a bit more mathematically. Specifically, today we'll be using a combinatorial technique called the inclusion-exclusion principle. In its simplest binary form, the inclusion-exclusion principle gives us a way to count the number of elements in some set by counting the elements of a few smaller sets. Specifically, consider two finite sets A and B, which may or may not have some elements in common. We can count the number of elements in A union B by counting the number of elements in A and B separately. But to do so, we end up double counting the elements in the intersection. So in order to compensate for this, we have to subtract the size of the intersection of A and B. That is, the size of A union B is equal to the size of A plus the size of B minus the size of the intersection. In our case, we're not trying to find the size of sets. Instead, we're trying to find the sum of sets of integers. But as it turns out, the same principle applies. If I want to find the sum of A union B, I can do it by finding the sum of A, adding in the sum of B, and then subtracting the sum we double counted from the intersection. So we can at least get rid of the set union operation with this principle. Let A be the set of multiples of 3 less than 1000, and let B be the set of multiples of 5 less than 1000. Then the sum of A union B is the answer to our programming challenge, and by the inclusion-exclusion principle, we know that this sum is equal to the sum of A plus the sum of B minus the sum of the intersection. Now consider the intersection of A and B. This is the set of all positive integers less than 1000 which are divisible by both 3 and 5. Basic number theory tells us that every number divisible by both 3 and 5 must be divisible by the least common multiple, or LCM, 15. And the converse is also true. Every multiple of 15 is clearly divisible by both 3 and 5. So the intersection of these two sets is just the multiples of 15 less than 1000. So we can simplify our Haskell program a bit to simply take a bunch of sums. We've eliminated the set union, but we still have those pesky lists. Fortunately, all three of these lists look relatively straightforward. Let's write them out mathematically. Consider our first set A, the set of multiples of 3 less than 1000. The sum of this set can be written as a summation of 3j, where j ranges from 1 up to some upper bound. That upper bound is the number of elements in the set A, which is equal to the number of multiples of 3 less than 1000, or equivalently, the number of multiples of 3 up to 999. We can write that concretely as the floor of 999 divided by 3. Now, basic arithmetic tells us we can pull out the 3, leaving us with 3 times a sum from 1 up to some constant. And we've encountered this particular summation many times by this point. This summation is a triangular number. In particular, it's the 333rd triangular number, since the floor of 999 divided by 3 is 333. So the sum of the set A is just 3 times the 333rd triangular number. We can follow the same logic for B and the set A intersect B. For B, we find that the sum is equal to 5 times the 199th triangular number, and for the intersection, we find that the sum is equal to 15 times the 66th triangular number. This allows us to simplify our formula quite a bit. Now, it may look like we still have some lists to generate in this program, but we actually don't. See, the concept of a triangular number is a well-known mathematical definition. So provided that the LLM behind Infinite Craft is familiar with the concept, we can simply get our argument numbers, like 333, 199, and 66, and craft them with the triangular number object to have the LLM obediently do the arithmetic for us. At this point, we actually have all of the pieces we need. We're going to come up with the word triangular number, generate a bunch of specific numerical constants, turn them into triangular numbers, and then take a few sums and differences. And with any luck, we'll get the answer we want. So let's get started. First, let's get triangular number. The obvious way to do that is to combine triangle and number. And fortunately, both of these words are very straightforward to get. I won't go through every recipe tree today, since some of them are fairly involved, but these are pretty short so we can get them quickly. Let's start with triangle. Water plus earth is plant, plus another earth is tree, plus water is river, plus earth is delta. On the other hand, earth plus wind is dust, plus earth is planet, and 2 planets make a star. Then star plus delta is triangle. Now let's do the same thing for number. We already have plant, and plant plus wind is dandelion, plus another plant is weed. From dandelion we can also add water to get wine, and water plus wine is holy water. Holy water plus fire is vampire, which is somewhat infamous in Infinite Craft for swallowing up a lot of words. But in our case, vampire plus weed gives us count, and 2 counts makes a number. And finally, triangle plus number is pyramid. Not quite what we wanted. And pyramid plus another number is sphinx, which is clearly in the wrong direction. We need a retry, sort of like when Infinite Craft added numbers incorrectly. We need a close synonym to triangle or number so we can try the same interaction. We can try combining different versions of pyramid or triangle with different versions of number or count. But Infinite Craft keeps getting hung up on the ancient Egyptian aspect of it, giving us mummy or sphinx in most cases. Instead, we'll do number plus count to get counting, triangle plus counting to get trigonometry, plus number to get math. Triangle plus math is Pythagoras, who together with triangle is hypotenuse. Pythagoras plus hypotenuse is Pythagorean theorem. Now this next one was really just guess and check, but Pythagorean theorem plus pyramid is trilateral. Trilateral plus number gets us back to Pythagoras, but trilateral plus counting gives us triangle number. Close enough, I suppose. Now we need to generate some numbers. I'm not going to go into detail on how I produced the constants 3, 5, 15, 66, 199, and 333. Suffice to say, it was just a bunch of tedious arithmetic and retries. A couple of the values didn't cooperate the first time around, which is why we'll be doing some of our math with Mario Party 199 instead of just the number 199. Now let's get some triangular numbers. We'll start with the smallest number. Triangle number plus 66 is 2,211, which is actually, ludicrously, somehow correct. Triangle number plus 333 is 55,611, which is again, somehow correct. Our Mario Party sequel gives us a bit more trouble. Triangle number plus Mario Party 199 is Triangle Twisters, which confused me at first. But it turns out that's the name of a minigame from Mario Party DS, so I see why the game got caught up on that. Fortunately, we can maneuver around it pretty easily. Mario Party 199 plus count is just Mario, but plus counting gives us 199 somehow. As long as we have enough synonyms for what we want to do, we can convince the engine that we're correct. And triangle number plus 199 is 19,900. So we're making progress. Now we need to multiply. I don't have a good way to multiply, so we'll just repeatedly add. 55,611 needs to be multiplied by 3, so we'll just add it to itself twice to get 166,833. 19,900 needs to be multiplied by 5. We will not add it to itself 4 times, as Infinite Craft tends to get a bit cranky when we just shove the same object on itself over and over again. Instead, we'll do a sort of repeated squaring. Add it to itself once to get 39,800, then add that to itself to get 79,600, and then add another 19,900 to that to get 99,500. Add 166,833 to that to get 266,333. Interestingly, the game seems to be more likely to get addition correct on larger numbers, whereas when we were working with 4 or 5-digit numbers, it was more likely to just invent a value. Now we need to multiply 2,211 by 15. Again, we want to minimize the number of addition operations, so we'll be repeating larger values whenever possible. I ended up taking a slightly odd route here, since the most straightforward approach of get 5 times 2211, then multiply by 3, ended up failing. But we get there in the end, and we get 33,165. Now we need to subtract. But subtraction is just addition by a negative. So take 33,165, add in the object negative, which can be obtained in a lot of ways, and then add 266,333 to get 233,168, the correct answer. And this solves Project Euler problem number 1 in Infinite Craft. Next time we'll be back on our usual schedule with problem number 27 in Yoke. Yeah, so in case it's not obvious yet, this is an April Fool's video. Turing completeness in Infinite Craft has, as of recording this, not yet been achieved. Though if we ever do find it, I'll certainly do a video on that. A lot of the Infinite Craft recipes in this video are faked, but the mathematics and arithmetic simplifications are real. We'll definitely be using the inclusion-exclusion principle in the future at some point, so stay tuned. See you all next time.